Assalamualaikum and hi, my name is Amir Hidayat bin Osman. I'm from Universiti Teknologi Mara. So I'm going to present my paper, which is Design and Analysis for the Gating and Risering System for Steel Sand Casting. Alright, so here are the contents: introduction, methodology, result discussion and conclusion. For the introduction, what is sand casting? So sand casting is a manufacturing process that uses sand to create a mold to produce shaped metals. Here is the configuration of the flask or container that is used to hold the sand. It consists of two parts, the cope and the drag. Inside the flask, it contains a cavity of any desired shape, the gating system, which consists of these components, and the risering system. So the process is simply any metal will be melted and then poured into the gating system, filled in the product's cavity, and the risering system for the excess metal. Then the metal will solidify and the casting is removed from the mold. So that's basically the sand casting process. Some of the example of casting products such as engine blocks, gears, brake drums and valve. So my project aims to propose gating and risering system for the case study. So I'll be looking at the gating and risering system design and then evaluate the effectiveness using the simulation tool and make some modification to improve the casting process and increase casting yield. So for the problem statement, what is the problem with sand casting process? Well, the first one is an improper gating and risering design can lead to casting defects. According to Raharjo et al. And Landach, about 90% of casting defects are due to issues with the gating and risering system, which highlighting the importance of proper gating system. As you can see in the picture, these are the common defects that could happen in sand casting by trial and error. So that's why my first objective is to establish a proper gating and risering system design for the steel casting case study. And then the next problem is how to reduce the trial and error in foundry, because to propose the gating and risering system, it requires money and time. So it can be solved by using the simulation tool, which can reduce the shop floor trial. Therefore, my second objective is to verify the effectiveness of the gating and risering system using computational simulation. And lastly, even though it is effective to produce a good product, it is also important that the gating and risering system needs to be optimally designed to reduce the material waste and also increase productivity. And therefore, I'm able to propose suitable gating and risering system for the case study. Alright, now for the methodology. Here's the flow process of my project. The project starts off by doing some literature review, and then I have to identify the case study from the technical drawing. I do the 3D modeling. There were two models, the product and the casting model. I'll explain later why. After that, based on the model, I designed the gating and risering system. So that's basically the first objective. For the second objective, the casting model is simulated in the simulation software and analyze the result. If the casting performance and the casting yield is passed, then I can propose the casting yield for the case study. And then I redesign the channel systems for the improved model and repeat the simulation process. Lastly, I evaluate the results and yield value, yield improvement, and compare the results. Alright, so let's start off with the case study. So I chose body globe valve, which is one of the components of globe valve, and it is used for regulating the flow of fluid through a pipeline. I chose this as a case study because in Malaysia, the production of valve is not so extensive. Based on OEC website, Malaysia export 288 million ringgit and import 404 million ringgit in valve during the first quarter 2024. And the Malaysia industrial valve market shows a decrease of negative 10.48% CAGR in 2021 over a period of 2017. So the study is beneficial to the local foundry to produce more valve and lessen the dependency from other countries. So here are the specs. The weight is 46.58 kilos and the material is medium carbon steel ASTM A216 WCB. The composition, density and melting point are as stated. For the 3D modeling, as I mentioned earlier about the two models, these models were created using the CATIA software. The product model is the actual product itself, while the casting model is a replica of casting product. Because in sand casting, it needs to consider what it called the pattern allowance, which is an intentional increase in dimension to compensate for various factors. And these are the factors: contraction, machining, and drafting. So basically, the casting model is a bit larger and a bit heavier compared to the product model. Now, the establishment of the gating and risering system. For the gating system, I use empirical approach, which I gathered formulas from previous studies and reliable sources, since there is no specific methods in designing the gating system. So these are the components. Unlike risering systems, there are several methods: change method, modulus, and shape factor. And I chose change method because it is a bit easy to understand, and it has a design riser verification through what it called the change curve, which it is used to determine the riser's performance. Alright, now I want to show the initial and improved design first for better understanding in the next section. So this is the initial model, which was designed based on the calculations and guideline. So these are the components. And then the improved design is the improved version after the simulation. So the significant difference between these two are the junctions at the running ingates area and the transition between the riser and the neck. The junction was changed from branch design to smooth corner, and the transition was changed from chamfered to curved design. The riser volume also has been reduced to minimize material waste. I'll explain in the next section. Alright, so here is the simulation setup inside Altair and SpyCast. The software is capable to read many types of CAD files, including this one from Katia. Even the software can create the 3D modeling using sketch and geometry features. And the setup is pretty simple, just 5 steps are required. The first one, define the cast part, and then select designated filling entrance, which is the sprue, define casting component, and tempering time, and mesh size, and then run. So that's basically the user interface is really simple and easy to understand. So in the result and discussion section, I only covered velocity during filling, solid fraction during solidification, and porosity as defects analysis, because these parameters are correlated with each other. So we'll go through one by one. Alright, so when looking at the velocity analysis, the gating system was the area that is exposed to high possibility of turbulence due to the small cross-sectional area and consists of a junction. So that's why we focus on the gating system only. Alright, so as you can see in the initial model, there were several areas that exceeded the critical threshold, which is 4.08 meter per second, especially at the runner and ingates. This is due to the wrong gating ratio used in the initial model. The cross-sectional area for the runner was not able to mitigate the high velocity during filling. The problem can cause turbulence flow and create gas entrapment within the casting. So I changed the gating ratio. I changed the gating configuration from pressurized to unpressurized, which is different gating ratio. And as you can see in the improved model, all the pinpoints were below the critical threshold of 2.18 meter per second. For the solid fraction during solidification, it is a proportion of solidified materials within the casting. The goal here is to achieve directional solidification, which the riser should be the last area to solidify. So the results show the solidification pattern in 4 different scenarios. The first 2 images were taken at the same time point, which was at the start and at 98 seconds to show the progress. The third image was taken when the liquid in the casting in the middle flange isolated from the riser, and the last image for the left and right flanges. So as you can see, the time taken for the molten metal to be isolated throughout all the flanges for the initial model was much earlier, leaving a large volume of isolated metal within the casting. This is due to the risers were not able to accommodate proper solidification pattern. This issue can cause porosity, as these metals can produce carbon monoxide gases and these gases weren't able to escape from the casting. So I modified the transition between the neck and the riser from chamfered to curved design to delay the bottleneck. So based on the improved model, although the isolated metal still present inside the casting for the improved model, but the volume is relatively low, making the solidification rate exceed the contraction rate. This can be verified through porosity analysis. Alright, lastly, porosity is a small void or air presence within the casting. The results show a porosity defect set to 90% of defect level, and as you can see, the porosity occurred on all the flanges for the initial model. As mentioned previously, it is due to the gas entrapment, which comes from the turbulence flow and improper solidification. So by modifying the gating and risering system for the improved model, the porosity was shifted towards the riser. Alright, now for the yield comparison. Based on the formula, basically the more volume of the gating system, the less yield value can be achieved. So it needs to be optimally designed. The casting weight for both designs remain the same. The gating system was slightly decreased 0.84 kilos from the initial design due to the smaller gating system overall. For the risering system, I managed to reduce the riser's volume by 19.21 kilos, which is about 63% from the initial model. I achieved this by optimizing the chains method. Therefore, I'm able to obtain a yield improvement of 17.65%. So for the conclusion, I'm able to obtain a yield improvement for body glove valve production while eliminating the casting defects. I also understand the importance of optimizing the material usage, as nowadays many manufacturers tend to focus on sustainability and cost reduction. And then by optimizing through simulation tool, the shop floor trial can be reduced and allow for more efficient production processes. Therefore, I'm able to propose the suitable gating and risering system for the globe valve. So that's all from me. Thank you.